Some of you may have noticed a video camera. I've been making a video today. It's not really for you. It's more for me and for Kaplan. They sometimes ask us to do videos so they can kind of see what we're doing, see how we're doing it. They may have suggestions or things for us to do things differently. All right, so let's start on, we're on page 429, circles, complex figures, and solids. And we'll start by reviewing the Kaplan method for math, which is on page 429. And Rohan, read that first part of the Kaplan method for math for us.
What is the question?
Yeah, we want to make sure we know what it is asking us. Rashmi, number 2.
What information am I given?
Yeah, keep going.
What information is provided in the question stem? In what format do the answers appear?
Good. And number 3, number 3, Ryan.
What can I do with the information?
Keep going.
A, picking numbers, B, back solving, C, straightforward.
Yeah, we've already seen all 3 of these different approaches kind of in action, and you're going to see them some more tonight. And then finally, number 4 is Sadiq. Yeah, which is basically kind of goes back to the first one. We want to make sure we're actually answering the question. So let's take a look at circles, and we're going to do a quick review of circles on page 430. So on the top of the, in that first box there, Sandra, if you'll read that first box, please.
A circle consists of points in a plane that are equidistant from a given point called the radius or center point?
Called the center, yeah. Equidistant from a point called the center. And see that next box, Adam.
Below that or next?
To the right.
There at 360 degrees in a circle.
Good, 360 degrees in a circle. Harith, the next box.
Radius.
Go ahead and read the whole thing.
The distance from the center to any point on the circle is called the radius.
Good. Rohan.
The distance across the circle through the center is called the diameter.
Good. Keisha, next box.
Diameter equals twice the radius?
Yeah, twice the radius. Diameter is 2 times the radius. Longest line in a circle, Rashmi.
Is the diameter?
Good. Formula for the circumference, Swati.
2 pi r or pi times the diameter.
Good. 2 pi r or pi times the diameter. And finally, the area for the, the formula for the area pi.
Pi r squared.
Good. Area is pi r squared. Notice a lot of students, they sometimes will kind of mash together the formula for the circumference and the area into something like 2 pi r squared. There is no 2 pi r squared formula. All right? Circumference is 2 pi r, area is pi r squared. All right. Okay, so now let's take some of this circle's information and apply it to a problem like number 1. Ryan, would you read that problem for us, please?
In the diagram, the diameter of the circle is 16 is long. If the circle is cut in half along the diameter, what is the total perimeter of the 2 pieces in the end?
Good. So now, what is the question in this one? What is it that we're looking for, Keisha?
What is the total perimeter of the 2 pieces?
Yeah, total perimeter of 2 pieces. So this is one where it's probably a good idea to go ahead and draw a picture of what the 2 pieces of the circle are going to look like if you cut it in half. All right, so we're looking for the total perimeter of these 2 pieces. And what information do we have to help us find this total perimeter? Ron?
We have that the diameter is 6.
Yeah, the diameter is 6 units. So this distance here is 6. This distance here is 6. So now if I only knew the whole rest of this piece here and the whole rest of this piece here, then I could add it to those 2 6 pieces and I'd be done. So what is this whole distance here and this whole distance here in terms of that picture?
Circumference.
It's the circumference of the circle, yeah. So I've got 6 plus 6 plus the circumference of the circle. And the circumference, I know a formula for the circumference, which is 2 pi r. And what's the radius of this circle? 3. The radius is 3. So 2 pi times 3. And that gives me 12 plus 6 pi. And I've got an answer choice there that's 12 plus 6 pi. Questions on this one? All right. Let's flip over to page 431. A couple of other things about circles. Hart, read that for us, please.
A line blank to a circle blank is the radius of the point of contact.
Right, and so, and it's not giving you a whole lot of information other than that picture there to the right, which appears to be a picture of a circle with a radius and a line up there and a little box there in the corner. So with that information, Swathi, what would you think might be what you would want to fill in the blanks on that one?
A line tangent to a circle is perpendicular to the radius of the point of
Excellent.
contact.
Yes, excellent. Tangent to a circle is perpendicular to the radius at the point of contact. And you almost always see this in the SAT. You'll always have questions on that are going to make use of this information. Like, for example, question number 2. Byron, read that for us, please.
In the figure above, line segment AD is tangent to the circle at point B, and line segment EG is tangent to the circle at point F. If BF equals 2, what is the area of the circle?
All right. So we've got this kind of complicated picture here. And we're told that these 2 points here are tangent to the circle at these points right here. So anytime I've got a line that is tangent to a circle, I know that I'm going to have a radius. If I draw a radius to that point, that radius is going to be perpendicular. So if I draw in two radiuses, two radii, then they're going to be perpendicular. I've already got a perpendicular symbol right here where these 2 lines intersect. So here I've got 3 perpendicular angles here, which means that this angle here is also going to be a right angle. And now I've got this line in here, which I'm told is 2. And now what is the question here? Sadiq, what am I looking for?
The area of the circle.
Yeah, I want to know the area of the circle. And I have a formula for the area of the circle, which is pi times r squared. So if I could just figure out the radius of the circle, I'd be in business. Well, it turns out I've just drawn in 2 radiuses of the circle. Here's one right here, here's one right here. And so what figure do I have now that I could use to find the radius of the circle, right?
An isosceles or a triangle.
Good, isosceles right triangle, which is this right here. So I've got R, I've got 2. Rohan, what might be a good way to figure out what R is?
Because it's a 45, 45, 90, root 2, like each radius is root 2.
Each radius is square root of 2. And how do you know it's going to be square root of 2?
Because that's the rule for like 45, 45.
Yeah. Rohan, for those of you who may not remember your special right triangles, Rohan is remembering that the ratio of the 2 legs to the hypotenuse of a 45, 45, 90 triangle is 1 to 1 to radical 2. So this radius has to be radical 2, because if you multiply it times radical 2, then you get this distance here, which is the hypotenuse of that circle, hypotenuse of that right triangle. So now once I know what r is, I just plug that in here. Pi times square root of 2 squared, which is 2 times pi. And I know the area of my circle is 2 times pi. Did anybody see another way? Let's say you looked at this picture and you're like, yeah, I know I want the radius, and I know this is a right triangle, but you didn't remember the 45, 45, 90 rule. What other way could we use to find the radius? Pythagorean theorem, yeah. R squared plus r squared equals 2 squared. That's going to be 2r squared equals 4. Divide both sides by 2. That gives me r squared equals 2. And r equals square root of 2. All right. Might take a little bit longer to do that calculation, but if you don't remember the 45, 45, 90 ratios, then that's going to be your best bet. Other questions on this one? All right. So let's flip over to page 432. And here we're going to talk about arcs and sectors and central angles. So if you will read that first box there for us, please, Byron.
The length of an arc as a fraction of a circle's circumference is equal to the degree measure of the corresponding central angle as a.
Any idea what goes in that blank? There's a little hint in that box there to the right, where it's got x over 360 equals arc length over circumference of the circle. Now, what it's looking for that that blank there, it's the measure of the corresponding central angle as a fraction of 360. And there's a picture that I want you to draw in there, right next to where that little formula is there on the right. Draw in this picture of a circle with an angle that has its vertex in the center of the circle. And what do you call this? What do you call an angle in a circle that's got its vertex at the center of the circle?
Central.
That's called a central angle. So if I call this central angle x, this piece of the circle right here, that's called an arc. So in that formula there, x over 360 equals arc length over circumference of the circle. This is the x they're talking about. That central angle is x. All right, so that next box down underneath there, Rosh, read that for us, please.
The area of a sector as a fraction of the circle's area is equal to the degree measure of the corresponding central angle as a... Is it the same thing?
It is exactly the same thing. As a fraction of 360. And so again, I want you to draw the same picture. A circle with a central angle. We'll call the central angle x. So now this time we're not talking about a formula for the arc length. We're talking about a formula for the area of a sector. And the area of a sector is that pie slice right there. That pizza slice. And you can see there's the formula right there. X over 360 equals the area of the sector divided by the area of the circle. So again, x is this central angle. That divided by 360 is equal to the area of the sector divided by the whole area of the circle. All right. So let's take a look at question number 3, which is going to use some of this information. Sadiq, read that for us, please.
The circle below has a diameter of 6 inches. What is the length in inches of the arc that has a central angle of 60 degrees?
Good. And so what is it that we're looking for, Swati, in this question?
The length of the arc.
Yeah, we're looking for arc length. And we've got a formula for arc length. That's that first one that's given up there. X over 360 equals arc length divided by the circumference. So in this particular question, we're looking for arc length, so we're looking for this piece right here. So what is the measure of our angle, our central angle in this circle, Sandra?
160 degrees.
60. So I got 60 over 360. Arc length is what I'm looking for. Let me call that A. Do I know the circumference of this circle, Ryan?
Yeah.
How do I know the circumference?
Because you know the diameter is 6, so you just do 6 times pi.
6 times pi. Yeah, the diameter, the circumference is pi times the diameter, or 2 pi times the radius, which is 6 pi. Well, now I've got a proportion that I can solve for A, which is my arc length. We reduce this and call this 1/6. 1/6 is arc length over 6 pi. If I cross multiply, 6 pi equals 6 times A. And A, my arc length, is equal to pi. Questions on this one?
Wait, could you do that again?
Yeah.
Sorry.
That's all right. Which part, Keisha?
Okay, like after you got the proportion, and then you do, yeah, and then how did you get 1/6?
So from here, once I got my proportion set up, I've just got one unknown. So all I'm doing is solving my proportion. So to solve a proportion, you cross multiply. Actually, first, before I did that, I reduced this 60 over 360 to 1/6. Then from here, I cross multiply. 6 times A is 6A, 1 times 6 pi is 6 pi. All right? And then from here, I just canceled or divided both sides by 6, and that gave me A. All right.
Thanks.
Other questions on this one? All right. Let's go on to page 433 and take a look at complex figures. Rashi, let me get you to read that first sentence there in the top of page 433.
Difficult geometry questions often contain complex figures. The key to answering these questions is to
Yeah, this was actually in from one of the videos on Smart Track. So if you didn't happen to see the video, you might not be entirely clear what they're looking for here. Anybody want to take a guess? The key to doing the complex problems, Ryan, go ahead.
Is it to first isolate those figures and then solve from the isolated figures?
No, but you're kind of on the right track. These so-called complex figures, they typically have like more than one picture in them. Like there's kind of multiple things in the diagram. And the key to solving these problems is to transfer information from one figure to the other. All right? And if you look at this figure that they've got drawn there right underneath that box, it looks something like this. And we're told one line here is parallel to this other line. And it asks what roles are played by line segment OQ in the figure below of the semicircle. All right, so I've got this line right here, and it asks me, well, what roles is it playing in the figure? So Byron, what's one role that this segment is playing in this figure? And I don't have this completely labeled, so you may want to look at yours down there. What's one thing that this segment, what's one thing that it's doing? One thing that it represents in here. This figure, let me ask it a different way. This segment right here is a part of what shape?
Triangle.
Yeah, which triangle?
QPO.
Part of triangle QPO. QPO. All right, so that's one thing that it's doing in there. Sadiq, what other role is it playing?
It's the same thing as OS, and it's the radius, isn't it?
It is, yes. It's a radius of what?
Circle.
Yeah, radius of, actually it's a radius of this semicircle. All right, so it's a side of triangle PQO. It's a radius of the semicircle. Rohan, what else?
It acts as a transversal.
A transversal. And now remind us, Rohan, what exactly is a transversal?
It's a line that intersects two parallel lines.
Yeah, actually it's a line that intersects any two lines, but yeah, very frequently it's two parallel lines. And we're told that these two lines here are parallel, and you can see that it is intersecting them, and so yes, it acts as a transversal for those two lines. Very good.
Wait, what's a transversal?
Very good.
What is it again, Rohan?
A transversal is a line that intersects through any two lines.
Yeah, it's just a line that intersects two or more other lines. And the two lines in particular are this line here, PQ and OS. And that segment there, OQ, intersects both of those lines. You may remember back from geometry, when you're doing stuff with parallel lines, when you have two parallel lines cut by a transversal, there are often many angles there that you can identify as being congruent or supplementary, and you often see that in figures. Now we can also say, Byron pointed out this was a part of this triangle QPO. Notice it's also a part of this triangle, which is triangle, what is that? QOR or QRO. All right. So this is kind of an example of what they mean when we're talking about transferring information from one figure to another. You might want to think of it's kind of a way of being flexible in your thinking. All right. So you don't want to look at this and just think, oh, this is just a part of this triangle right here. No, it's a lot more than that. So being able to go between all those different figures, all right, is very helpful. So let's take a look at question number 4. Keisha, read that for us.
In the figure above, rectangle EFGH is inscribed in the circle with the center Q and radius 13. If the length of FG is 10, what is the area of rectangle EFGH.
All right, so what is it that we're looking for, Adnan, in this question?
The area of the rectangle.
Yeah. And what's the formula for the area of a rectangle, Hart?
Based on height.
Yeah. And do I know the base and the height for this particular rectangle?
Yes. Or I mean, you can solve it.
All right. One of them I actually do know. Which one do I know, Ryan?
10.
Yeah, I'm told that 10, we'll call that the height. So I actually do know that part. This is 10. And I also know something else about this figure, which is what, Byron? It is, it's cut into 2 triangles. In fact, it's cut into 2 right triangles. That might be handy.
The radius.
The radius, yeah, I know that the radius of the circle, which it turns out is,
10.
yeah, it's going to be half of that
Oh,
diagonal.
just
so
kidding,
that-
13.
Yeah, so this radius is 13, which means this whole piece here is going to be how long?
26.
It's going to be 26. So now I know the diagonal of my rectangle. I know the height of my rectangle. Ryan, how's that going to help?
Pythagorean triplet, 10, 24, 26.
Excellent. Right away, Ryan could see that the base of the rectangle is going to be 24 because he remembers that one of the Pythagorean triplets is 5, 12, 13. And if you multiply each of those by 2, you get 10, 24, 26. And that 24 is the other leg of a right triangle. Now, if you didn't happen to remember the Pythagorean triplets, then you could find this in another way, which is how, Sandra?
Pythagorean theorem.
Yeah, you just use the Pythagorean theorem. 10 squared plus this squared equals 26 squared, and you'll get that this is 24.
How'd you get 20?
How'd I get which?
Okay, wait. You got 10. How'd you get 24?
24. Ryan, how'd you get 24 again?
Pythagorean triplet.
It's Pythagorean triplet. The Pythagorean triplets, remember there's a couple of kind of the main ones, a 3, 4, 5 triangle, and then there's the 5, 10, excuse me, the 5, 12, 13 triangle. 5, 12, 13 triangle, if you multiply each one of these by 2, you get 10, 24, 26, and that's what this one is.
Oh, okay.
All right. And again, if you don't happen to remember those Pythagorean triplets, you can always use the Pythagorean theorem. So once we know that that's 24, our area, 24 times 10, and the area of that rectangle is 200. Other questions on this one? All right. Let's go on to page 434, and we're going to talk a little about solids. Sadiq, volume of a rectangular solid is?
Length times width times height.
Good. Volume of a right circular cylinder, Swati.
1/3, no, it's pi r squared times the height.
Excellent. Pi r squared times the height. And the surface area of a rectangular solid, notice we're talking about surface area, not volume, is, Rohan?
The sum of the area of all the bases.
Yeah, the sum of the area of all the sides. Let's say that we have this rectangular solid that's given in that picture up there at the top. So go ahead and give it to me in like in a formula.
2 nm plus 2 np plus 2 np.
Oh, you're looking at that bottom one. Yeah, I was looking for the one in that top box there.
Oh.
Length, width, and height.
Oh, right. So 2 lw.
There you go.
Plus 2 lh.
Yeah,
Plus 2 wl.
there you go.
I mean,
Length times width is the area of one of the faces. Length times height is the area of the other
it
face.
should be h.
H.
My bad.
And width times height is the area of another face. You got 2 of these, you got 2 of these, and you got 2 of these. You add them all up, and that's your surface area. All right. So let's take a look at question number 5 there. Read that question for us, please, Rush.
In the figures above, the volume of the cube is 64, and the volume of the rectangular box is 224. What is the area of the base of the rectangular box?
All right. And so we're looking for, Byron, in this problem,
The area of the base of the rectangular box.
area of the base of the rectangular box. And I got 2 key pieces of information here. Adnan, what are they?
That the volume of the cube is 64 and the volume of the rectangle is 224.
Yeah. So if I start with the volume of the cube, I know that it is 64. And for that particular cube, I can say that the volume of that cube is going to be m to the third power. That is m times m. Length times width times height. Which tells me that I can solve this for the value of m. And what's going to be the value of m?
4.
If m cubed is 64, yeah, it's just going to be the cube root of 64, which is 4. So now I know what m is. Now I can go to the formula for the volume of the box, which is going to be m times n times p. Well, I know what m is, so I can plug that in here. And I also know what the volume of the box is. What's the volume of the box?
224.
224. Well, now I've got an equation, and notice if I divide both sides of this by 4, then I'm going to have n times p. And 224 divided by 4 is 56. And what exactly is n times p?
The area of the base of.
Yeah, that's the area of the base of that rectangular box, n times p. So that's what I'm looking for, which is 56. Questions on this one? All right. Page 435. One more thing to know about solids. As with complex figures problems, many difficult solids problems are best attacked how?
Step by step.
Step by step is not a bad idea, yeah. Although we're actually looking for the same thing that we talked about at the top of page 433 with complex figures.
Transfer information from one piece to the other.
Say it again, Swati?
Transfer information from one piece to another.
Yes, transferring information from one piece of the or from one shape in the figure to another. All right. In particular, you want to look for familiar shapes within the figure, and very often right triangles are going to jump out at you from within the figure. So let's take a look at question number 6. Sadiq, read that question for us, please.
In the cube above, the length of the piece edge is 3. What is the straight line distance from vertex A to vertex B?
All right, so here I've got a cube. And I'm told that the length of an edge of my cube is 3. And I'm asked to find this straight line distance from A to B. All right. Now this one, you kind of have to use your imagination here because I'm drawing a 3-dimensional figure on a 2-dimensional space. But I'm looking for this distance from A to B. And if you look, you might be able to see that I have got a triangle. In fact, I've got a right triangle that I can draw inside this cube. All right. I'm looking for this distance from A to B. Well, if I knew the length of this leg of the right triangle, which actually I do know that one, if I also could figure out the length of this leg of that right triangle, then I could use my Pythagorean theorem, and I could solve for this distance from A to B. Well, let's see if we can figure out what those lengths might be. This right triangle here, let me call this point C, this corner down here, so I'll have something to talk about. So now I'm talking about triangle ACB. Put this triangle over here. There's ACB, and this is 3. I'm looking for this distance right here. We call that X. And if I could figure out what this length was, then I could solve that for X. So is there some way that I could figure out what that length is? Anybody see another triangle here that might help us out? You see it, Sandra?
Use the Pythagorean theorem on the bottom triangle and find out the length, and
Yes.
then do the Pythagorean theorem for the bigger one.
Yes, excellent. This bottom triangle here, and I've kind of drawn it in red here. And in fact, let me get this one another. Let me call this corner here, we'll call that K. Now I've got another triangle down here, and as Sandra's pointing out, I know the length of this side of this triangle. I know the length of this side of it. I can find out what the hypotenuse of that right triangle is. That hypotenuse is the same as this length here. If I can transfer that information to the other figure, then I'll be in business. So my red triangle is, draw this one over here. This is triangle BKC. This is 3. This is 3. So what's the length of this distance here, BC? Or let me ask, how can I get this distance here, BC? Ryan?
45, 45, 90.
It's a 45, 45, 90. So this is going to be
3 root 2.
3 radical 2. And again, if you don't, if those ratios are still not very, comfortable for you, you can always use the Pythagorean theorem. 3 squared plus 3 squared equals, call that BC squared. That's going to be 9 plus 9, which is 18. And square root of 18 is going to be 3 radical 2. So now I know what this is. 3 radical 2. So I just want to solve for x. How can I do that? Sandra, you want to finish it for us?
You just do the Pythagorean theorem again.
Yeah,
so
go ahead.
3 squared plus 3 squared, 2 squared equals c squared.
Equals,
Or x squared. Sorry.
yeah, I'll call it x squared.
Yeah.
And the rest is just some arithmetic.
Yeah.
9. 3 radical 2 squared, that's going to be 9 times 2, which is 18. That's going to be 27. And x is going to be square root of 27, which is 3 radical 3. And now I know what x is. Right?
There's a trick. If it's a cube, because all sides are equal, any non-adjacent vertices, the distance will be whatever your side is times root 3.
One.
Which is what we figured out in the long run.
Yeah.
Yeah. So you're saying if you happen to know that rule, if you happen to know that trick, then you guys, I guess, could save yourself a lot of calculation.
A lot.
Exactly. So that's maybe handy to know. And of course, if you don't happen to remember that, well, then you got to go keep it along. Anybody else remember that rule?
Yeah.
Other than Ryan? Where'd you learn that, Ryan?
School.
That was my first guess. Geometry class? Pre-calc?
It was for math competition.
A math competition. Very nice. Okay, other questions on this one? All right. So now we got some guided group work. Your groups are on the board here. And let me write your pages in your course book. Let's see, group 1 and group 2, y'all are both on page 438. And group 3, you are on page 458. So let's go ahead and get in our groups, and we'll get started on the group work.